So in this video, we're going to continue those very cumulative exercises of exercise 2330, in exercise 2330. And remember, there are three things that you should be familiar with before you approach these exercises. They're the aromatic substitution reactions from a previous chapter. They are the activating and deactivating and orthoparadirecting and metadirecting effects of different branches from the aromatic substitution chapter. And then there are the reactions of diazonium ions from this chapter. So once you have all those memorized, that's just the first step. The second step is learning how to piece them together. And that's what we're trying to do in these exercises. So in this one, we start out with just pure benzene, nothing on it. And we end up with a tert-butyl group added and also a carboxylic acid added. Now, the tert-butyl group, that's an alkyl group. We're forming a new carbon-to-carbon bond onto a benzene ring. That is a Friedel-Crafts reaction. So we could narrow that down to either Friedel-Crafts alkylation or Friedel-Crafts acylation. In this case, because we have a tert-butyl group, there's no way that that would rearrange. Remember that the liability with the Friedel-Crafts alkylation is that you end up forming a carbocation on the carbon that attaches to the benzene ring. And if that could rearrange, well, then you won't get the branch that you want. And so you'd have to use Friedel-Crafts acylation. But here, this carbon, if it were a carbocation, would not rearrange. It would be a tertiary carbocation, and it would be in the most stable position possible. So we could add that tert-butyl group by doing a Friedel-Crafts alkylation. And that would involve adding a tert-butyl chloride with aluminum chloride, AlCl3. And that would add that group onto the benzene ring. So that's what the recipe we would need to add the tert-butyl group. As for the carboxylic acid, that one is a little trickier. Perhaps the most straightforward way of making that would be from a carboxylic acid derivative, namely a nitrile. If, instead of this molecule, we had a nitrile here, well, then we could hydrolyze it, use hydronium, H3O+, and that would turn that into a carboxylic acid, as we learned in the carboxylic acid chapter. But how can we get a cyano group on there? I might have said nitrile a second ago. I meant cyano. It's not a nitro group, it's a nitrile. Once it adds onto a carbon chain as a group all by itself, it's called a cyano group. We learned how to put a cyano group onto a benzene ring in this chapter. We could put a cyano group, we could have it as a nucleophile that attacks a diazonium ion and displaces the two nitrogens. So if we had a diazonium ion, then we could do a Sandmeyer reaction. You could treat that with copper cyanide, CuCN, and that would replace the diazonium ion with the cyano group. So that's what we could do here. We could treat this with copper cyanide. So if we had a diazonium ion, we could get the cyano group on there, and if we had the cyano group, we could hydrolyze it and turn it into a carboxylic acid. But how do we get the diazonium ion? Well, we only know one way to make a diazonium ion, and that is to make it from a primary amine. So if we had the same molecule, but first, or instead of the diazonium ion, we had a primary amine, an NH2, well, then we could add sodium nitrite and HCl, that classic recipe, and get the diazonium ion out of it. But how can we get a primary amine on a benzene ring? Well, we've seen this before. It's a two-step procedure. We could get it in one step if we had the nitro group. So if instead of NH2 you had NO2, you could reduce it using the iron and HCl that we have here. You could also use zinc and HCl, but iron and HCl would accomplish that transformation. So if we treat this with iron and HCl, the nitro group will turn into a primary amine. But how do we get the nitro group on there? And the way you get the nitro group is nitration, and that involves nitric acid in sulfuric acid. And that's in this review of the previous reactions also. So it's a two-step procedure to get the primary amine. First, you use nitric acid and sulfuric acid, that adds the nitro group on. Then you use either iron or zinc and HCl, and that reduces it to a primary amine. Once you have the primary amine, you can make a diazonium salt out of it, and then you could do a Sandmeyer reaction to get the cyano group, and then you can do the hydrolysis, acid-catalyzed hydrolysis of a nitrile with H3O+, and that'll turn it into a carboxylic acid. So those are the reagents we need in order to add this carboxylic acid on. But remember that whenever you add things onto benzene, it's not just a question of what you add, it's a question of when you add things. You have to think about the order that you add things in. We want these two branches to be para to each other. Now that carboxylic acid, that is a deactivator. Remember that if you have a pi bond to an electronegative atom conjugated with the ring, that's a deactivator and a meta-director. So we have a pi bond to an electronegative atom, and it's conjugated to the ring, double, single, double, right? Alternating to single and double bonds. So this is a meta-director, so we don't want to put that on first. How about the tert-butyl group? The tert-butyl group is an alkyl group, and that is an activator, and therefore an ortho-para-director. So we could put that on first. So first, we could take just pure benzene, react it with this Friedel-Crafts alkylation. That would put the tert-butyl group onto the benzene ring. And then once we have that group there, that's an ortho-para-director. If we put the nitro group on after that, it will either go to the ortho or para positions. But notice that the tert-butyl group is really bulky, so the ortho positions are not going to be preferable, and the nitro group would add to the para position. Then you can reduce it to get the primary amine, turn that into your diazonium ion, do the Sandmeyer reaction, and hydrolyze the nitrile. So overall, there are several steps for this synthesis. The first step is a Friedel-Crafts alkylation. It puts the tert-butyl group on. That's an ortho-para-director, and so we can put a nitro group on the para position by doing nitration, HNO3 and H2SO4. Then we reduce the nitro group to a primary amine. Then we turn the primary amine into a diazonium ion. Then we do the Sandmeyer reaction to replace the diazonium ion with a cyano group. And then we hydrolyze the cyano group to get the carboxylic acid. And that would be an efficient synthesis for making this transformation, starting with pure benzene and getting this para-tert-butyl benzoic acid. Okay, let's try E. In E, we start with pure benzene again, and we end up adding two different things, a chlorine and a fluorine. Oops. Now, fluorine is a tricky thing to add, but it is one of the things we learned how to do in this chapter. Fluorination. You could add a fluorine onto a ring if only you have a diazonium ion first. You can treat it with HBF4. So, if we had HBF4 and we treated a diazonium ion with that, one of the fluorine nucleophiles would displace the diazonium ion, and you'd get your fluorine on the ring. But how can we get a diazonium ion on a benzene ring? And hopefully now we've seen this process 2 times before. Hopefully now it's becoming more rote. And you'll notice something about doing these synthesis exercises, which is the more you do them, the easier they become. It's like playing an instrument. The more times you see changes, you build connections between reactions, and you start to see larger arcs. You don't see the individual reactions as completely separate things. You see how they can combine to create common transformations. A common transformation is putting a diazonium ion onto a benzene ring. And the way we've seen how to do that is, the only way we know to make the diazonium ion is from a primary amine. So we would treat that with sodium nitrite and HCl, and we could get a primary amine from a nitro group. Oops. If we reduce it with iron and HCl, and we could get the nitro group on by doing nitration. Adding nitric acid and sulfuric acid. So this process here is one that we saw in the previous example. We did that in this example. We had that same series of reactions to put a diazonium ion onto a benzene ring. Now, we need to start with benzene, not with chlorobenzene. So how could we put a chlorine onto a benzene ring? That was one of the reactions we learned how to do in the aromatic substitution chapter. Chlorination. You'd add Cl2 and AlCl3, and that puts a chlorine onto a benzene ring. So we can treat that original benzene with molecular chlorine and aluminum chloride. That will give us this molecule. And chlorine is a good one to add first rather than fluorine, even though they're both ortho-para-directing. Let's unpack that for a second. We need these branches to be para to each other. Right? It's always important when you're adding things onto benzene to consider how they add. These are both halogens. Let's think about the halogens. The halogens were weak deactivators, but ortho-para-directors. So both of these, both the fluorine and the chlorine, would direct the other to go on the ortho and the para positions. So technically you could put either first, but putting chlorine on first is more efficient because chlorine is a bigger atom. Remember, atoms get bigger as you go down and to the left on the periodic table, and chlorine is just below fluorine. So chlorine is a bigger atom, which means it would be harder, once you put the chlorine on there, it would be harder for the nitro group that we add to add onto the ortho positions because of how big chlorine is. If you had a smaller atom like fluorine, which is the size of a hydrogen, chlorine is the size of a methyl group. If you had fluorine on there, then there's more room for the nitro groups to add ortho, and you'll have a bigger mess in your beaker. So you had the chlorine first. That sort of crowds out the ortho position. Then you do nitration. You put the NO2 on the para position, because chlorine is an ortho-para director. Then you reduce that to the primary amine, turn the primary amine into the diazonium ion, and replace the diazonium ion with a fluorine using HbF4. So altogether, first chlorination, second on the para position, nitration, then reduce the nitro group, turn it into a diazonium ion, and replace the diazonium ion with a fluorine. And so 5 steps overall to create this transformation. All right, let's try one more. F. Here, we're replacing a chlorine with a bromine. Now, it would be easy enough to put a bromine on a benzene ring. You could, if you just started with benzene, then you could brominate it, so Br2 and FeBr3, for example. But in order to do that, we would have to get rid of the chlorine first. And we don't know any ways to get rid of a chlorine. Unless we do a substitution reaction. Chlorine is a good leaving group. Maybe we can use a really strong base. Maybe, and you might remember the reaction elimination addition. It produced the benzyne intermediate. What you would need is a strong base. Here, a useful one would be sodium amide. And ultimately, you do something like a substitution reaction. The chlorine gets replaced by the NH2, but the mechanism is a little strange. Like I said, you form that benzyne intermediate in this elimination addition reaction. So if that sounds unfamiliar, if it sounds a little hazy, and you want to go back and review it, look for the video that draws the mechanism for elimination addition in the aromatic substitution chapter. You would have drawn the mechanism for that on a previous test. Now, I think in that video, the base we use is OH minus hydroxide, but it would work just as well with this amide, this NH2. And the NH2 is useful because we can turn it into a diazonium ion, adding the classic sodium nitrite and HCl. And then we can replace it with bromine, this leaving group with bromine, by doing a Sandmeyer reaction. Right? One of these Sandmeyer reactions, we can use this copper-1 bromide, and the bromine will displace the diazonium ion. So, copper-1 bromide, and that's it. Not too many steps here. So the first step is to do that kind of weird elimination addition. It doesn't come up too much, but you could see when it's needed, it can be really useful. That would displace the chlorine leaving group and bring in this strong base nucleophile amide. Then you would turn that primary amine, right? The nitrogen is only bonded to one carbon, into a diazonium ion by adding sodium nitrite and HCl. And then we do a Sandmeyer reaction. Basically, the bromine comes in as a nucleophile and kicks this amazing leaving group off, and we end up with our product. So in this video and the last video combined, we looked at the reactions of these diazonium ions. And if they're attached to benzene, which they almost always are to help stabilize them, otherwise if they're just on a regular alkane, they're pretty explosive, and so not very useful. But if the diazonium ion is attached to a benzene ring, it's called an Aryldiazonium ion. And that's what we've dealt with here. We've looked at multi-step syntheses involving these Aryldiazonium ions. It required us to remember the aromatic substitution reactions from a previous chapter and also the directing effects. Orthopara for the activating groups and also the halogens. Meta for the other deactivating groups. And then we also had to learn these new reactions of diazonium ions. Learning those was the first step. The second step is making connections between those reactions by working through these very critical thinking, cumulative type exercises.